In this video, we're going to have a look at the inclusive gateway of the BPMN standard. The inclusive gateway is also called the OR gateway. Let's look at the syntax of the split of an OR gateway. Once a token arrives at an OR split gateway, then immediately a decision will be made based on data. That means that all outgoing sequence flows of the OR split must have data conditions attached to them. Let's look at what this construct would mean. Let's assume that A holds but B does not. Once a token arrives at the OR split, then immediately a decision is made based on data. And in this case, because A holds and B does not, a token will be produced on the outgoing sequence flow that goes to the top. If A does not hold but B holds, then on receipt of a token, the OR split will again immediately take a decision, and in this case, because only B holds, a token will be produced on the sequence flow annotated with B. If A and B both hold, then on receipt of a token of its incoming sequence flow, the OR split will produce a token on both its outgoing sequence flows, both the one annotated with A and with B. And then the remainder of the process behaves as if these were parallel. If neither A nor B holds and a token arrives at the OR split, then it will throw an error message, so this is a behavioral issue. Thus, in order to guarantee that the OR split can always fire and has no behavioral issues, we need to ensure that A or B holds. Alternatively, we can annotate one of the outgoing sequence flows of the OR split with a default, as shown here. What are the semantics of this default? In case A or B holds, nothing changes and the default will not be activated. However, when neither A nor B hold, then on receipt of a token, the OR split will produce a token on the sequence flow that is the default. Let's look at the OR join. In the BPMN standard, the so-called path-based semantics are given to the OR join. In the path-based semantics, an OR join can fire if two conditions hold. First of all, at least one incoming sequence flow must have a token. Second, for every path of sequence flows that start with a sequence flow that has a token and end at the OR join, and that last sequence flow in that path must not have a token. Right? For each of those paths, there must exist another path that start at the same token, go to the same OR join, but the last sequence flow of that path must not have a token. So informally, for every token that can still go to the OR join, it must also be possible to go to the OR join to a sequence flow that already has a token. Let's look at some illustrations. In this case, the OR join has a token on its upper incoming sequence flow, and its bottom incoming sequence flow will not have a token. Therefore, the OR join can fire. Let's illustrate this definition a bit. Here we have an OR join, and this OR join has two incoming sequence flows, of which the top one currently has a token. Now we look at paths in the other sequence flows. Is there a token that can still come? And the answer here is no. So, technically speaking, there is no path P, and therefore for every path P something holds, right? Empty domain. So therefore the OR join can fire. Let's look at another example. In this model, the OR join has a token on its upper incoming sequence flow. Therefore, condition 1 is satisfied. For condition 2, there is a path P, namely this path, that starts with a sequence flow with a token on it, namely here, and it ends with an empty sequence flow before the OR join. So there is a path P. However, there is no path Q. However, there is no path Q with which this token can come to the OR join on an occupied incoming sequence flow. Therefore, in this situation, the OR join must wait. Let's look at another example. In this case, the OR join has a token on one of its incoming sequence flows, the top one, so condition 1 is satisfied. For condition 2, we see again a path P that starts with a token and ends with an empty incoming sequence flow of the OR join. And for each such path, for each path P, there is another path Q which goes through here, which takes the token to an already occupied incoming sequence flow of the OR join. So in this case, for every such path P, there is a path Q, and therefore the OR join can fire. Let's look at a small example. In this model part, let's say that a token arrives here from the left at the parallel split. The parallel split fires, produces 2 tokens. Now let's say that the exclusive gateway at the top takes a decision, and that decision is that A holds. Next, the bottom gateway fires, and therefore we arrive at this marking. At this point, the OR join has one token on its incoming sequence flow, and there is a path P by which another token could arrive at the OR join, and there is no path Q by which this token can go to an already filled incoming sequence flow of the OR join, and hence the OR join waits. Then let's say that the exclusive choice gateway decides that B does not hold and directs the token up. In that case, the OR join will consider that it has a token on its incoming sequence flow, so condition 1 is satisfied. Condition 2 is also satisfied because there is no path P by which another token could walk to this OR join. Hence, the OR join can fire. Let's look at another example. In this example, let's say that the bottom gateway fires and we end up in this marking. In this marking, the OR join has a token on its incoming sequence flow, thus the first condition is satisfied, and the second condition, we have a path P from a token. There's also a path Q by which the token could come to an already occupied part of the OR join. So in this marking, the OR join can fire. Let's say that by some means of randomness, the exclusive gateway fires first, based on that A is true. In this situation, we already saw it in the previous example, the OR join has an incoming sequence flow that has a token, so condition 1 is fulfilled. However, for the second condition, there is a path P by which this token can come to the OR join, but there is no path Q by which that token could go to an already filled incoming sequence flow of the OR join. So there is no Q here. Therefore, in this marking, the OR join will wait. Then let's say that the second exclusive gateway on the top takes a decision based on B, and now we are in this marking, and of course in this marking the OR join can fire. So for this single model, we had 2 moments in which the OR join could fire. The first was before the decision between A or not A, and the second was after the decision between B and not B. So for the same data and the same input, we have 2 different decision points. Let's play out both of these situations and see what happens with the final marking. So let's say that in the top left, we fire the OR join because we established it could fire. And then the decision between A and not A is made, and the decision between B and not B is made. So let's assume that A and B both hold. Now we are in the situation where the OR join has an incoming sequence flow that has a token, and there is no path P for another token that might still come. So the OR join may fire and produce a second token on its outcoming sequence flow. On the right model, there the OR join can fire and produce a token on its outgoing sequence flow. This example shows that we may have a different outcome if the data is equivalent, right? A and B both hold in both situations, and for the same input marking. So the output marking of this model fragment purely depends on which of the gateways takes a decision first. Let's look at what happens when we make two OR joins dependent on one each other. In this small model fragment, we have two OR joins that depend on each other, so the output of OR join 1 goes to OR join 2, and the output of OR join 2 goes to the input of OR join 1. If we are in this marking with a token on an incoming sequence flow of OR join 1, then we follow the path-based semantics. And given that there is no other token in the model, there can also never be any path P, and therefore the OR join can fire. And let's say that the model then ends normally. In this example, both OR join 1 and OR join 2 have an incoming token on one of their incoming sequence flows. Let's look at OR join 1. According to the path-based semantics, condition 1 is satisfied because it has a token on one of its incoming sequence flows. For condition 2, there is a path P that starts in this token and then ends up in an empty sequence flow going into OR join 1. So this is path P. However, there is no path Q that would bring the token to an already filled incoming sequence flow of the OR join, and therefore OR join 1 has to wait. For OR join 2, we apply a similar reasoning. Condition 1 is satisfied because it has a token on one of its incoming sequence flows, but condition 2 does not hold because there is a path P that arrives at an empty incoming sequence flow of OR join 2, but there is no path Q that brings that token to an already occupied incoming sequence flow of OR join 2. Hence, OR join 2 has to wait as well. In other words, this model is in a deadlock. While these path-based semantics are what's written in the BPMN 2.0 standard, they have a few downsides that we've seen. First of all, the outcome may depend on the moment of choice of gateways, which are supposed to take decisions based on data immediately. Second, if these OR joins are modeled in such a way that they are dependent on each other, then we have potential deadlocks. To alleviate these issues at least partially, other semantics for OR joins have been defined in literature. In another video, we're going to have a look at a different type of semantics, namely the friendly bus driver semantics.